You're speaking? I'm not speaking. I don't know what you're talking about. All right, great. So it's a pleasure to welcome Nathan Srebro from the Toyota Technological Institute in Chicago. Nathan graduated from MIT, and he made like very influential contributions to machine learning and AI research, from maximum margin factorization and applications to collaborative filtering and recommender systems, to implicit regularization, which was a very powerful and inspiring framework to understand what's going on with deep neural networks. He received numerous awards for his work. He proposed many solutions to very challenging problems, but he's also known for asking very difficult questions during talks on problems that few people can solve, maybe him. And so today he's going to speak about weak to strong generalization in random feature models.
Okay. Thanks, Zaid. Yeah, I ask hard questions because I don't know the answers. So then other smart people that are actually smart can solve them, and they do sometimes. Okay, thanks. It's great being here. It's an amazing room, I should say. I think I've been in this building before, but I don't remember this view. Okay, so I'm going to talk about some work on weak to strong generalization. I'm going to introduce what I mean in a second. I just want to say this is joint work with my student Marko, and also the Kaifeng, Dingli, Sanjeev, and Zhiyuan. So with the question we're looking at, we're basically asking is, can a student outdo his teacher? So in particular, think of the following setting. We have a weak teacher that learns actually from reality, from labels. So the weak teacher is going to get supervision from our ground truth target, and learns by matching those labels. And then we have a student that's maybe much bigger, stronger, smarter than the teacher, but never actually sees the real world. So the student only gets supervision from the weak teacher. Okay, so the only thing that the student sees is what the weak teacher tells him. Anybody, by the way, recognize the weak teacher? This is see how some of you are, maybe now. Oh, so this is Dan Quayle. I don't know if you use him. Okay. What? What is it? It's a weird picture. I thought it was fitting, though. Okay. So Marko, which is really an amazing student, only unfortunately gets supervision from his teacher, but maybe even for a weaker teacher, and only gets sometimes labels that are wrong or just incorrect. And the question is, so Marko just trains to fit the labels that he gets. And then the question is, can Marko actually learn to be better than the teacher? What I mean by better, they were measuring, even though Marko's training time only minimizes the loss versus the teacher, what we're measuring in the end is how well can Marko fit the reality, the actual ground truth. So we're comparing how well the teacher fits the actual ground truth and how well the student fits the ground truth. And the question is, can the student actually fit the ground truth better than the teacher that taught him? Okay. So this is a basic question here. And I should say this was gained a lot of attention recently through a very influential paper from OpenAI. And in OpenAI view, the reason that OpenAI talked about this question is the way they're viewing it is they eventually want to train students that are smarter or more powerful than humans, whatever that means. I'm not sure actually what that means. And unfortunately, they're going to be trained by humans. And the question is, can this strong student then become better? How can they become better than the humans that trained them? Okay? And so this is the setting, but the way they actually studied this is not with a weak human and a strong machine, but just with two machines, a weak machine and a strong machine, so the same as we're going to study it. We train a weak machine based on reality, and then a strong machine based on supervision from this weak machine. And in the OpenAI case in particular, they had some experiments, and they trained a GPT-2 size model on various tasks, and then they train the GPT-4 model, but just on the supervision from the GPT-2 labels. And what they observed is indeed the GPT-4 model that was only trained through the GPT-2 model was better than the GPT-2 model that trained it. So the student was in fact better than the teacher. One of the questions posed is, how does this happen? Can we understand it and quantify it? So we'll try to understand that, but before that, I want to go back a bit, and we have to be a bit careful about what do we mean here by the strong student. In what sense is a student stronger or smarter than the teacher? Like, in what way are they better? And in order to, and really, that'll get us to how surprising this is at all. And also in terms of how new it is. So OpenAI talked about this phenomena of a human teaching a machine to be better than it. This is actually not so new. In fact, we go back to the very first paper that mentioned at least machine learning, that explicitly talked about machine learning, 1959 papers by Arthur Samuel on using machine learning to play checkers. Then already then, Arthur Samuel, there's many things in this paper, by the way, that are spot on 60 years later or 70 years later. But one of the things that Arthur Samuel said in the abstract of that paper pointed out that the machine is superhuman. And the machine that's trained can, in fact, be better than the human that trained it. So it learns to play better than the human that programmed it. Okay? And even though this is not like some big GPT-4 model which is achieving intelligence with I don't know how many billion parameters, this is a checker playing model with I think 16 parameters chosen out of 48, I think. So maybe let's call it 48 parameters. Okay? And so how did this, so let's try to understand exactly what happens here, and let's go back even to the checkers. I mean, how did this machine, it's kind of not surprising to us. I mean, I don't think anybody in this room is too surprised that, but with this Arthur Samuel's superintelligence result. So let's try to understand how different ways in which you can achieve this, not necessarily superintelligent, but where you can be better than your teacher. Okay? So there's several mechanisms for that. So one maybe, which is the obvious one, well, I know maybe all of them is obvious, but at least for checkers, you can just do better search, better test time compute. Right? So I can explain to you the rules of checkers. The rules themselves are not so complicated. And then once you understand the rules, then if I only think 2 steps ahead and you think 10 steps ahead, then you're going to play better than me. Okay? So this actually doesn't have too much to do with learning, but when we're talking about a learned system being better, Arthur Samuel's checkers system being better than the human, it's not clear if this is actually due to learning or is it just due to doing better search. And that's true also for the systems we use now, because a lot of what's happening is either explicit or implicit test time compute. So we have to be able to separate between these test time search, test time compute issues, and maybe learning issues. Okay? Another thing that's related to that, which is definitely happening also already in Arthur Samuel's 1959 checkers players, is that if I can actually, once you teach me the rule of checkers, so Arthur Samuel is actually in his paper trained a board evaluator. So something takes a board and evaluates, is this a good position for the paper that the person is about to play? And this board evaluator, even though it only had 48 parameters or 16 sparse 48 parameters, was better than the human that trained him. And so it was actually learning that's better. And how can you achieve that? Well, how did he train the board evaluator? It trained it using self-play, basically. Right? So he had he had the computer playing games against itself, or different versions of itself, actually. And through that, you get observations about, you see what the outcome of the game would be, and based on that, you can work back to evaluate, to get a signal as to whether this board position is good or not. Okay? And this is kind of, both of these are kind of variants of in this way, even with no actual, even though your supervision is pretty stupid, it just tells you whether you won or lost the game, you can learn to play very well. And this is really kind of maybe a, yes?
This is a little different than, I'm just thinking back to the very first slide you gave, right? And you said the only information I have is
I think that's true. I think that's true. So the only, if I teach you to play checkers, the only information you're going to have is from me. All I tell you, so initially you don't know how to play checkers. You don't even know what it means to win or to lose. You just like, you have a game piece and you remove things randomly. The only supervision I tell you is I slap your, well, first of all, I slap your hand if you do an illegal move. Okay, that's pretty easy. You're going to figure out the rules. But I know the rules also, so you're not being superhuman in that. And then I just tell you whether you won or lost. So this is what I'm telling you. So it falls in that framework that all the supervision you're getting is from me. And nevertheless, you can learn to be better than me, because you can learn to better than me predict which move is going to be good. Okay, and so in both of these, I mean, maybe another way to think about this is in both ways. What's going on is that the problem has a very simple verifier. And that you're not going to be better than me in terms of the verifier. The verifier in this case is, did you win or lose? You're not going to be better than me at figuring out at the end of the game if somebody lost or won. But the search here is difficult. So what you're going to do is, first of all, you can be better than me doing the search by just putting compute over it. But you also can learn to be better. You can learn to be better at search also. You can learn to be better at like predicting which move you have to do. Okay? So basically, I mean, the mechanism at play here is just a reinforcement learning mechanism, right? So you have a very weak, the supervision is very simple, but you're learning how to play this game. Does that answer the question? Okay. So the point I want to make is in both of these mechanisms, so they are a bit different, but in both of them, the key is we have a separation between the complexity of verification and the complexity of the search, which again is something that should be very familiar to all of us. And in those cases, you definitely, you can learn just by interaction. Okay, but these are two cases. But it seems that, like in GPT, there's another thing that's going on. So if, for example, I teach Zaid here, and I think Zaid, and I teach him names of places in France. So I visit some place in France, and then I tell Zaid the place I visited. Zaid would, even though I'm pretty bad at like, not even pronouncing correctly, but remembering names of places in French, I'll be a very bad teacher. But Zaid will probably, based on my really poor, I'm not going to try to demonstrate this now, very poor supervision, be able to actually pronounce these names of places much better. And the reason is because Zaid has much better prior knowledge here, right? So Zaid actually, you can think of this prior knowledge that he gained either because he was programmed with better prior knowledge, if maybe we programmed the machine with better features, or through pre-training, right? So Zaid was heavily pre-trained on French, much more than I was. No? Heavily pre-trained on French, and so developed much better features. And in that case also, we should not be surprised that like a student can be better than a teacher. If we take it to this extreme, like, I can teach Zaid French. And if we go now in 3 minutes, I'm going to teach Zaid French. And what do you know? After 3 minutes of training, Zaid is a better French speaker than I am, okay? And so again, it's not at all surprising that the student can be better than the teacher if the student already has this prior knowledge. You go back to the GPT-4 versus GPT-2 experiments, it's very difficult to understand, to distinguish between that is what's going on, or is it really that just Zaid is so much smarter than me that in 3 minutes he can like learn to be better than me. Okay? Because even though the tasks themselves were tasks that the GPT-4 didn't see exactly that task, GPT-4, in the experiments they took a pre-trained GPT-4 and trained the pre-trained GPT-4 on some natural language tasks based on the GPT-2 supervision, but it's possible the GPT-4, but definitely it had better features, but maybe it also almost knew those tasks. Okay, maybe it could even do them zero shot. Okay, okay. So this is another kind of mechanism for weak to strong. But really, what we're trying to understand is whether if I teach something to Zaid, Zaid can be better than me just because I don't know, Zaid is more powerful, maybe he has like a bigger brain, right? Just more parameters. So can you take is it possible to get this weak to strong generalization where really I don't have any, the weak learner, sorry, the strong student is not going to do any additional search. This is not a situation we have this verification search setting. It's just a pure kind of prediction problem. And the only advantage of the strong student is that it's bigger. Okay, so imagine this, I have a small neural network, I have a big neural network, I'm going to train the small neural network on reality, and then I'm going to train the big neural network on the outputs of the small neural network. And there's nothing like these neural networks are the same, except from one is bigger than the other. It's not like there's better prior knowledge going into here. There's the same kind of prior knowledge, just more. That's clear? Okay, so So this is what we're going to look at, and we're going to specifically look at two-layer networks. And so this is already like this is a simple model, but we're going to look at whether we can get weak to strong generalization, even a simpler model. What we're going to do is we're going to take the bottom layer of this network to be fixed during training, so just initialized randomly. And during training, we're only going to train the top layer weights. Okay, so now it depends. I don't know, depending on your background, how you prefer to think about it. You can think of it as a two-layer network where I initialize the bottom randomly and train over the top, or you can just think of it as a random feature model. So I have some distribution over features, and I just sample a subset of those features and train a linear predictor in those features. Yes, Jamie, what's wrong?
Why is it upside down?
What is upside down?
X is on the bottom and f of t is on the top. And like the first layer should be the one that's...
No, it always goes from the first layer is always in the bottom. I think that's also something where some people are going to take it differently, the same as...
Standard in circuit complexity.
Yeah.
Okay.
Okay. To me, this is more natural. Okay. Okay. So the setting user claim. So I draw. Okay. So again, so how does the training look like? I have a student with MT. I'm going to draw teacher with MT. I'm going to draw the random features for the teacher. I'm going to train the top layer. And to make it even more generous for the teacher and also easier to analyze, the teacher just trains optimally on the distribution. So you can think of it as just training with infinite data and infinite runtime. The only thing limiting the teacher is the size of its brain, right? It's like the number of parameters or number of features, okay? And then we take the student, and the student is going to be much bigger than the teacher, right? So again, the only difference is it has more of these hidden units, more random features. And in fact, we're going to take the student to be infinite wide. So the student is going to have even infinite number of hidden units. And we're going to train the student by minimizing the loss versus the teacher. Okay, so now, if I actually did this, if I just minimized, what would happen here if I really just took the student and I trained the student to minimize the loss versus the teacher? What would the student learn? Exactly the teacher, right? So if Zaid, I started teaching Zaid how to pronounce names of places in France, and Zaid was a very good student. Eventually, it'll be hard work, but eventually Zaid will replicate my really bad French pronunciation, okay? And that kind of defeats the point here, right? So we don't want the student to actually replicate the teacher. And so what we're going to do, we're going to train the student with early stopping. Okay, so just with gradient, with the gradient descent early stopping, or actually gradient flow with early stopping. So we're just going to take, think of this as gradient descent with infinitesimal, with the infinitesimal step size, and we're just going to do that for a while. So this is the same as with Zaid. After we spend several years together just with my bad French, eventually he'll get it. But if we just do it for 10 minutes, then he'll still retain, he'll hopefully succeed in pronouncing the name of the city, towns, even if he didn't know about it before, and with good accent. What?
Quit early.
And quit early, yeah. Quitting early is good. Okay. And I should note that this is also something that came up in the OpenAI experiment. So they trained the GPT-4 model with early stopping versus GPT-2, and they pointed out that that was important in their training. Yes, question? You can ask.
I mean, I guess the thought is like maybe that's some kind of regularization
No.
against overfitting.
So of course it's regularization. Yeah. So it's definitely regularization against overfitting the teacher, because we said we don't want to overfit the teacher. We can overfit the teacher, but then we're not going to be any better than the teacher. We're just going to imitate it. And so it is exactly regularization. But still, the question is, how can this allow me to be better than the student? Sorry, how can it allow the student to be better than the teacher? Because, yeah, I'm regularizing, but again, the only training signal I get here is from the teacher. How can I actually be better than the teacher? I don't have any, it's not, unlike the situation with Zaid, it's not that I have, the student has any more knowledge.
Right.
It's just more parameters. So what?
The teacher hasn't overfit the distribution.
The teacher can't overfit, no, the teacher didn't overfit because it's training on the target, right? So it's not, okay, so another issue, well, actually, I was planning to come in at the end. It's also possible to get weak to strong generalization if the teacher did something stupid. Like if the teacher overfit or underfit or did all kinds of stuff like that, then you can also get weak to strong. You can kind of correct. But this is not the case here. The teacher really, given that it's like limited brain size, the teacher is doing the best thing it can, right? It's really getting the best approximation for reality that you can get with the number of features it has. Okay? Yes?
I agree that this is definitely the most interesting setting. But like, did they do anything like this in the GPT experiments? Like, how do you can't like, you can't really decouple like the pre-training.
No, I know, I agree. So I think that it's important to decouple. So I mean, I'll show you both experiments and theory. So this is that look at exactly this setting. Okay. Good. So what I can show in the setting. So what we can show that indeed in this case, I mean, I should ask you: do you think that you'll get your weak to strong generalization? But if you have any basic test taking skills, then you should, of course, say that there is. Yes.
Just a very minor thing. There was a paper a few years ago about noisy student. I don't know if you guys are familiar with it, but as the name suggests, there's an image classification, and they train a model to do image classification, and then they use that to pseudo label a lot of unlabeled data, and then retrain a larger model on top of the now labeled unlabeled data. And if you just don't add any noise, then you get exactly the same thing, but you just learn this feature again. But so they added noise to the.
Oh, so what is this paper? I'm not
it's
sure.
called noisy student.
Okay, maybe I'm not sure I've seen. Okay. Okay. So let me tell you what we can show in this case. So what we can show in this case is indeed you can get the student can become better than the teacher and much more so. So let's first of all look at a setting at a ReLU network. So this this activation function is ReLU activation, and everything else is Gaussian. So input Gaussian and input random weights. And in this case, what we can show is that in fact the student can become in some sense arbitrarily better than the teacher. So the ratio of the student error to the teacher error can be arbitrarily close to 0. It can get an arbitrarily high improvement here. So in particular in terms of the performance recovery gap that Burns introduced, I mean if you haven't seen this specific ratio before, it's not so important, but it can drive this gap to 1, which, so this looks at the teacher loss minus the student loss, so how much how much am the student getting of a teacher divided by how much the best possible student trained in reality can do versus a teacher. So 1 basically says that the student is in some sense as good as if it was trained on reality. Okay? But there's something misleading about these ratios because when we see a ratio that goes to 0, we can ask, okay, but by how much? When I can quantify that as well, what I can tell you is that the student can be polynomially better than the teacher with an exponent of at least 1.49. At least that's what we can prove. Okay, so not only can the gap be arbitrarily close to 0, but actually I can have a higher rate in some sense. Okay, so this is for, yeah.
So wait, there's no sample complexity.
There's no samples. Okay, right. So as I'm presenting now, there's no samples. This is all about approximation. So the teacher is trained on infinite data, and the student is trained by gradient flow on the population with a target label. So you can think of it as what happens. So there's several things here I send to infinity. I send the teacher, the amount of training data for the teacher, the number of units for the student. I send the step size to 0, and I send the amount of data in the student to teacher to infinity. You can make all of these like finite, but large enough if you want. But even if, in some sense, I think the result is even stronger when they're infinite, right? So this is, make sense? Yeah, and it's definitely easier to present. Yeah.
How does this depend on like the stopping time?
The what?
The stopping time?
Okay, so this is with, that's a good question. So this is with an optimal stopping time. So there exists a stopping time that gets this result. We don't have a theoretical analysis of how things deteriorate for different stopping times and how robust it is, but I'll show you soon in experiments how it depends on the stopping time. Okay, the result as I'm presenting now is there exists a stopping time that achieves this improvement. Okay, yeah.
Interpretation of stopping time is like depends on some validation set.
Let me show you the results in the stopping time. Okay, so let me just say that we can get better than this. So this is in a ReLU network. You can get even a stronger result in a linear network with a shaped covariance. So if you have a linear network and the input distribution instead of being spherical has a few coordinates which with high variance and a bunch of coordinates with low variance. So like a small kind of signal part and a very large additional bunch of junk features. Then in that case, we again get the gap going to 0. I mean, we can't get this better than 0, right, this ratio. But now the student is quadratically better than the teacher. Okay? Okay, and we can see this empirically, and then empirically we can also see this effect of the stopping time. So what we see here, this is first of all the relationship between the teacher error and the student error, and in fact we get, this is a log-log, no, sorry, this is not a log-log, this is a linear plot, and we get the best polynomial fit here is basically quadratic, and for the ReLU case, we actually get an exponent of about 1.85. I think we did it a bit more carefully and narrowed it out to 1.82 or so. I mean, the exponent here is definitely, I mean, this is very crude, this lower bound. It's definitely, the exponent is lower than 2. I don't know exactly what it is. If somebody is, I think this can be interesting. It's beyond kind of our current, our team's, maybe skills to exactly narrow down this. Okay, so, and then you asked about the stopping time. So here I'm showing you the errors. This is for different teacher widths. What the error is a function of the stopping time. And when in particular what I'm showing you is what's here, okay, so actually these two graphs are different. Here I'm showing you, do I achieve my quadratic improvement? And we can see that there is, especially for white teachers, there's actually it's pretty robust. Again, this is not supported by our analysis, but empirically it seems it's pretty robust. There's a wide range of stopping times here. And remember that the time axis here is logarithmic. So there's a very wide range of times in which I actually get generalization. So it seems that, in the beginning I just don't fit anything. And then I actually get good generalization. I get good generalization with this quadratic improvement for a while, and only in the very end do I overfit my teacher. And here, for ReLUs, what I'm showing you, so this line would mean no improvement at all, and what I'm showing you that I am getting an improvement here, it's still fairly robust, but not super robust. It's not like I have, it's relatively easy to choose a good stopping time here. And it's, in particular, generalizes reasonably well across different widths. And again, I should emphasize, we don't know how to analyze this. We don't know in particular how to analyze the stopping time as a function of the width so carefully as to show this. Okay, so is the phenomena clear? This question so far? Okay, and that answers your questions about the stopping time, I hope? Okay, okay, so how do we get this quadratic improvement? So let's try to understand what's going on here, and let's focus. It'll be easier for us to look at the linear case first. So this is the linear case. I have again a linear network with this shape covariance. I have a few directions with high variance and a bunch of directions with small variance. So this is the input variance, and the signal is going to be supported on this directions with high variance. Okay, so definitely the signal is related to the input distribution. That makes sense. I mean, that's when you need to get good learning at all. Okay, but now let's first of all see what does the teacher do. Okay, so the teacher is going to learn based on some random projection, low-dimensional random projection of this input. So really, you just want to use the first 3 coordinates, but the first 3 coordinates by themselves are not available to the teacher. Right? The teacher just sees some random directions that are not exactly aligned with those 3 coordinates. So in order to capture what happens the first 3 coordinates, the teacher has to project those first 3 coordinates into its the space that it has available. And in order to do that, it has to use some of the noise components as well. Okay? And so the teacher model is going to look maybe something like this. It's going to approximate the signal reasonably, but also have some noise over here. Okay, so there's 2 sources of noise here. This is the noise here in which the teacher is missing the signal, missing a bit in the signal. And then there's the noise here from all these like low variance junk directions. Okay, okay, so now let's see what the student is going to do. So the student, in this case, is going to be infinitely wide and is going to do gradient flow on W. But if the student is infinitely wide, then the student is still going to learn a linear model. So this is the activations here are linear, so everything is linear. Both the student is linear and the teacher is linear. I'm showing you here the model as a function of the input dimension, the inputs x. Okay? And the thing is that when m goes to infinity, then since u is orthonormal, then I'm going to learn this, I'm going to optimize over W, but I'm really learning a linear model in X. And since U is orthonormal, doing gradient descent on W and doing gradient descent on beta is the same thing. Like it's as if I'm just learning a linear function of the input dimensionality directly. Okay? And we know how gradient flow behaves. So how does gradient flow behave? Okay? So gradient flow works, so the directions with higher variance are going to learn first. Okay, so there's two ways to think about it. I don't know if you prefer thinking about it forward rather than backward. So in terms of the forward dynamic, I'm going to start with a zero predictor, and then I'm first going to learn the components with the highest variance, okay, because then I kind of get, my gradient is largest, and then I'm going to learn the components with lowest variance. Okay, another way to think about it is early stop gradient descent has a shrinkage effect. Okay, so it's a bit like ridge regression. Actually, it's an even more severe effect than ridge regression, but the amount of shrinkage depends on the variance in each component. So in particular, if I stop at time t, and for a component with variance lambda, the shrinkage is 1 minus e to the negative lambda I times t. So the higher the variance, the less shrinkage. Lower variance, I get more shrinkage faster. Okay? So that means that these components are going to be shrunk less than these components. Okay? And now, in how much faster? Well, it depends on this gap. So if I push this gap, I make this gap very high, okay, I can choose the stopping time such that I barely shrink these components, and I completely kill these components, or almost completely kill up to infinitesimal. Okay, so this is how the student is going to look like. The student is going to take all these is going to shrink everything towards zero. Everything is pulled down towards zero, but these in the low variance direction are going to be pulled down almost completely to zero. So I just eliminated this noise, and on the signal part, they're also going to be taken to zero. So I do lose here also, but I only lose a tiny bit because I only shrink a tiny bit. Right? So this way, the student can be better than the teacher. Right? The student lost a bit of error here, but gained a lot, or rather, removed all this error and also only introduced a tiny bit of error here. Yes?
Wait, did the fact that MS is infinity come in this?
Okay, the fact that MS is infinity came in for the fact that what the student does gradient flow in W, and what I'm saying gradient flow in W is the same as gradient flow on beta. That's as if, or that's one way of saying it. Another way of saying it, what's really important here is what is the kernel on the features? Like what is the kernel on this layer? Okay, and so the kernel, it's an empirical kernel. It depends on the data, but as the amount of data goes to infinity, the kernel becomes dependent just on input distribution here. Okay, so does that answer the question? So of course, if you have large number of features, it's going to be close enough, and things are still going to be fine, right? But okay, great. And then
that makes analysis easier, but doesn't help the fact that you're killing the signal.
No, it does help. The student is in fact going to be best when it goes to infinity. Another way to think about it is, so what is the student gaining here? We said that the student doesn't have any more knowledge. I was very careful not to use the word inductive bias, because the student does have, even though the student doesn't have more knowledge, it does have better inductive bias. So in some sense, in what sense? So the real inductive bias here comes from having infinite features. That's also what you should think about neural networks. The real network you should use, the real kind of inductive bias networks, is from infinite width networks. I mean, I think that's real. By the way, when we use networks as an aside, they really think that the objects working with is infinite real networks in the same way that when we write code all the time, we use real numbers. Although that's like, anybody of you ever programmed something involving real numbers?
Real numbers?
Real numbers. No, of course not. You can't. It's infinite objects. What you use is some discrete approximation of these real numbers. But you work with like a long enough discrete approximation with 64 bits of precision that you can pretend as if they're actually continuous. And probably with neural networks, it's the same thing, right? The real thing is you just have a finite truncation of an infinite networks. And so in the same sense that if you're with real numbers, the more precision you get a better approximation. This is also what's, I think, happening, in some sense, what's happening here. The real object here is the inductive bias given by the distribution over the features, like having infinite features. What I do is I actually settle for a finite network because, I don't know, that's what I can handle in my computer. And so what I have is, it's not so much that I have limiting my knowledge, but I have an inductive bias, which is an approximation of the real inductive bias. And the student being wider has a better approximation for the inductive bias. The teacher has a worse approximation of the same inductive bias. So now answering Zhiyuan's question, yes, the ideal thing would have to be the real inductive bias, which would correspond to infinite features. Does that answer your questions? Okay, excellent. Okay, so okay, let's oh wait, I didn't. And now, so this is for the linear case, and now, also related to something already told Zhiyuan, what happens in the ReLU case? So basically the same thing, but what we should look at now, the same story happens, but the same story happens And instead of looking at the variance of the different input components, what you should look at, the relevant thing to look at, is the variance at this layer, which corresponds to the kernel, the effective kernel that you're using, and what you have to tell the exact same story, but everything is in the eigendecomposition of that kernel. So you can represent your target function, your teacher, and your student in the eigenbasis of the kernel. And the correspondence things with the variances are the spectrum of the kernel, the eigenvalues of the kernel. So now, in order to do the analysis in the ReLU case, so this was relatively easy analysis. In order to do the analysis in the ReLU case, so there's two things here. I'm not telling you also here how we got exactly to square. One part is you have to, we can analyze in terms of how well the teacher kernel is aligned with the target. We can analyze how much improvement you'd get. So this is a deterministic part. And then there's like a random metrics theory part, which says for a particular distribution, how does the random teacher kernel look like? Okay, and that's where we get a lot of loosenesses. And maybe you guys can do a better job than us. Okay, let's go back to a bit more to the ground. Okay, so what's going on here? So instead of telling you how I exactly got, so here I hopefully help you understand why the student is getting a benefit here and where this benefit is coming from. Maybe I didn't tell you exactly what that quadratic benefit. So to me, maybe it's hard to think why it is quadratic. Both this is in high dimensions. My high dimensional intuition is it's very hard for me to get high dimensional intuitions. And second is, instead I'll show you a lower bound. It's somehow always easier for me to understand lower bounds. I find much more, tell you the story often much better than the upper bound. So what lower bound? So what we can show is you can ask, we got with this particular input distribution, in a particular setting, we've got quadratic improvement. Can you do better? Maybe you can get quartic improvement. Maybe you can get, I don't know, the student can be the teacher to the power of 7. Okay? Okay, so it turns out you can't. And what we can show is, in fact, quadratic is the best that you can. So we can bound the student loss, if everything, I should say here, is normalized correctly, that the null loss is 0. You can say that the student loss can be is never going to be better than quadratic in the teacher loss. Okay? And this holds for any random feature model. In fact, this is much, much more general than random feature models. So you can design some other random feature models, some other activation and get this, but this is much more general than random feature models. This is actually a deterministic statement that holds for any student teacher and any teacher features and any student features. So no matter how you design the features, your teacher has some feature space. Maybe it's learned based on prior knowledge or whatever. I don't care. Any feature space that you have, deterministic or random, that the teacher has, and any other much better, much higher dimensional, better inductive bias, whatever feature space the student has, if we repeat the same procedure, like the teacher learns optimally, the student learns from the teacher, and then you cannot get better than a quadratic improvement. And in fact, this lower bound is even more generic. So the only property we need, we don't need this to be like an optimal linear predictor. We don't need to be gradient flow. All we need is for the teacher and the student to be shrink optimal. What does that mean? So let's look at the teacher first. Then I'm going to learn some teacher, and all I need to say is that I cannot improve the teacher in terms of its training objective. I cannot make the teacher better on the target just by scaling it down. Okay? And this is a very natural property, right? I mean, if you could improve, we said the teacher does something sensible, right? If you can improve just by scaling yourself down, then you should do it. And in particular, and then so this is for the student, the teacher and the student, same thing, would, again, the student cannot improve their objective by just shrinking down, okay? And
by
yeah.
shrinking, you just mean like uniformly?
By just multiplying by scalar. You cannot take your prediction and multiply everything by 0.7 and be better. Okay, it makes sense? Because it's a very, very weak requirement. Okay, so in particular, this is satisfied by gradient flow. It's any time if you optimize, if you have a convex hypothesis class, you're just optimizing over a convex set, like a subspace, for example. You'll definitely get this. Doesn't have to be a subspace. Any type of convex set importantly contains the origin, because you have to like shrink towards the origin. And in particular, or alternatively, adding a convex regularizer. You can add any convex regularizer. Like if you say that we said here the student has to regularize somehow. If you regularize it using any convex regularizer, it doesn't have to be L2. It can be L1, whatever you want. Like anything convex, basically, would satisfy the shrinkage optimality. And with the shrinkage optimality, again, you cannot get better than quadratic improvement. Yes, question?
Yes, I have a question about the stopping time. Like if
if you look at the stopping time, it's scaling logarithmically in the dimension, in the number of...
in number of features, yes. Yeah.
So isn't that a bit pessimistic?
So no, okay, so because we're looking gradient flow, then time, remember the time is a bit of a fluid concept here. It's continuous time, but time doesn't necessarily mean number of iterations, right? So I don't know if it's, okay. Okay, okay, so in particular, what this means is that this gives us a limit, but it tells us something we cannot do. We might have hoped that we can have a really dumb teacher that's like really dumb. It's only like marginally better than nothing, okay? And that'll teach a student to be perfect, right? But what this says is we cannot have that, right? So I cannot have it in a strong way. In order for the student to have a diminishing error, the teacher has also a diminishing error. So I have to have, I can be quadratically better, but it's still, to drive my error to zero, I also have to have a teacher that with error goes to zero. And conversely, if the teacher is only a bit better than nothing, the student is also going to be maybe a bit less, but only a bit better than nothing, right? So I cannot take a teacher that's a bit better than nothing and get a student that's much better than nothing, okay? So I don't have this kind of boosting. I don't have this like type of phenomenon of boosting that we take a weak predictor that's only marginally better than chance and get a strong predictor out of it that's arbitrarily close to zero. Question?
Yeah, sorry, it's a naive question, but let's say my inductive bias is so strong for my student that its whole hypothesis based just as the correct.
Excellent. Let's hold on to that for a second, okay? So here, just a second, okay? Okay, so, okay, and, okay, maybe I'll already answer you, but I'll get to that soon. So note that I have a requirement here that I'll get there soon, that the origin has to be in my hypothesis class. So I have to shrink towards zero. If I'm shrinking, if I have a bias towards some other place, then that's okay. We'll see how that looks in a second, okay? Okay, so so this is in contrast to boosting. It's also in contrast to some other, I don't know, maybe people are familiar with a paper with a somewhat similar setup to ours in classification, but maybe finite data. But the big difference there is that the teacher is not optimal. The teacher actually overfits. And when the teacher overfits, then they're not shrink optimal. Okay? And in that case, in fact, you can get arbitrary benefit because basically what's doing, the student is effectively correcting for the overfitting for the of the student. Okay, and now just going to the comment here. So crucial to this lower bound is technically what we have to require is that I'm shrinking towards zero in terms of this convex training that my hypothesis class includes zero or the minimizer of my regularizer is at zero. Okay, so that happens if I learn features and then use those features. When it's not going to happen is if I have a pre-trained model and I start optimizing from that pre-trained model, because now I'm shrinking towards that pre-trained model. So that is what I would call specific inductive bias. So if you have generic inductive bias, you just learn features, this lower bound holds. But if you have very specific inductive bias, then the lower bound doesn't hold. And you can get arbitrary improvement because, of course, the teacher, the student, the pre-trained student can already be better than the teacher. Okay. Okay, so let's see how much time do I have? I have like 10 minutes?
15 minutes.
15 minutes, excellent. Okay, so let's look at this lower bound. I think that gives some intuition for what's going on here. Okay, so let's look at the lower bound. So let's take the teacher to be over here. So this is just an arbitrary point in space. So this is the teacher. What I'm drawing to you is, think of this as the teacher in the space of functions, okay? And I'm looking at the space and the geometry that corresponds to inner products with respect to the data. So in particular, distances in this space corresponds to the loss, right? So the distance between the origin and the distance, the loss is the distance to f star. Okay? So distance between the origin and f star is just the loss of the null predictor, right? That's kind of the norm of f star, and I take that to be normalized to be 1. Okay? Okay. So now what I'm going to do is first I'm going to learn the teacher. Okay? So I'm going to learn a teacher maybe on the subspace. Okay? And so first of all, I can say, well, maybe this is going to be my teacher. And I claim that this cannot be my teacher. Why not? Why can't this not be my teacher? This is not a legitimate teacher.
Shrinkage.
Shrink optimal. So why is it not shrink optimal? How can I... Right, so I can get, just by shrinking down towards 0, I can actually get closer to my to the target. Because remember, the distances on this slide, on this screen, corresponds to losses. Okay? So, right, so this is loss, and I can improve it just by going down. So in particular, on this subspace, this is the closest point to f star, and I'll be shrink optimal. If I'm here, I'm shrink optimal. If I'm here, in fact, I'm optimal with respect to scaling both up and down. Shrink optimal just says that I don't gain by shrinking down. So this is the set of shrink optimal predictors here, right? So any of these predictors are shrink optimal. These predictors are not shrink optimal. So my teacher can only be here, okay? So in particular, there's a right angle here, and if you think of what is the location of all the possible shrink optimal teachers, it's exactly in the ball that's between the target and the origin, so in this purple ball. So this is where my teacher is allowed to be. Okay, and this makes sense, like my teacher would never be over here because then it's better to predict 0. Okay, okay, is this clear? Okay, so this is where my teacher can be. So let's say my teacher is here, for example. Okay, so this is the loss of the teacher. Now where can my student be? So my student has to be shrink optimal with respect to the teacher. Okay? So the same arguments apply, and we can say that the student has to be in the ball between the teacher and the origin. Okay? And you're seeing here the origin plays an important role in all of this. Okay? So this is where the student can be. And now you're down to like a geometry question of like what's in this ball, which is the point that's closest to f star, that has the smallest error. And that point, of course, the projection of f star to this ball, so this is this point. And now you have to do some, okay, I have to admit this is where some of my co-authors and myself have differences. I could only do it with algebra. Like I did the analytic geometry here of writing the equations, deriving it. They somehow immediately saw it geometrically. But this is just a geometric question of, the ratio between this distance and this distance, if this is a ball, and this is another ball between the point in this ball and the origin. And it turns out when you do either the algebra or apply some geometry, then this is the equation you get here, just applying Pythagoras twice, I think. Okay. Okay. So this gives us a lower bound. Is this clear? Okay. Now, so this is the lower bound. Okay? And this also you can see from here that maybe you can't see exactly this expression, but you can see that you can get arbitrary improvement. You can't suddenly take the student to be extremely, extremely close to f star because this would be outside this ball, right? Okay, let me also use this figure to try to understand what's going on here a bit better with the inductive biases, because note that what I drew here, I just want to clarify, this is not the hypothesis class. It's not that the student is optimizing over the set, okay? If the student was optimizing the set, it would just choose ft, right? Because it's optimizing distance of t. It's just that what I'm showing you is for anything possible you're optimizing, I can guarantee to you, just based on shrink optimality, that you'd see in this ball. Okay?
Also not obvious to me why you want the student to be shrink optimal with respect to the teacher.
Well, what I'm saying is not that you want to, but it's going to be, because it's a student, the only thing the student is doing is optimizing with respect to the teacher loss. In any reasonable way of optimizing that, you're going to be shrink optimal.
Right, but if you knew that you didn't care about.
Okay, I would argue that even if you insist, I take a shrink optimal and then I say, okay, I'm going to take something and then multiply it, then unless I had some magical way of knowing in which direction I have to multiply, there's.
I guess my point is, if you know the teacher's stupid, it's not obvious to this is another form of regularizing.
I think I can. Let's talk about that later. But as what I'm claiming is all these training methods of training on the teacher are going to be shrink optimal. Okay, fine. Yeah. So let's talk later. I think you can. Okay. So okay. So how does this actually work? Okay. So what I have is I have a hypothesis class for this teacher. For example, I have some features for the teacher which defines a linear subspace. So like this linear subspace. Again, you should think of it as a high-dimensional linear subspace. I only have 2 dimensions to work with here. So think of this line as like a 3 billion dimensional linear subspace. Okay, and now I train on this linear subspace, so I find something optimal in this linear subspace, which means that I project f star into linear subspace. So this is my teacher. Great. Okay, what about my student? So one way to think about my student is I have the student. So I know my student is going to end up inside here, but that's actually not what I see. What I see is the hypothesis class for the student, or the feature space for the student, which again defines a linear subspace. Okay, so one way to think about it, this is the student linear subspace. Okay, and now I can maybe project to here, and my student will be here. Okay, but that's actually not what happens, because remember that our student subspace actually subsumes the teacher subspace. Okay, so this picture is wrong. It's not that this would be correct if maybe I have a small teacher in some direction and an equally small student, but maybe with better features. Okay, but that's not what we're talking about. We're talking about more features. And in particular, we know we shouldn't project because then I'll just stay in space, right? So the student subspace is really the entire thing. A better way of drawing the student inductive bias is the student has some feature space, and it's going to do L2 regularization in that feature space, or gradient flow regularization in that feature space. And so effectively, the student, what it has is like this effective regularizer that it wants to be, the shape of this ellipsoid captures the shape of the student features in this data inner product. And what I want is to be, the student wants to be close to the origin in this geometry. Okay? So what I'm actually going to do, the way the student is going to look like, you can also think of the hypothesis class as being one of these ellipsoid, and which ellipsoid depends on your regularization parameter. So the student is going to project the teacher to one of these ellipsoids, maybe to here. Okay, so this is if the student was doing ridge regression, okay, like with some regularization parameter. What we're studying, and you can get the same guarantees also for ridge regression. We're not studying ridge regression here. We're studying early stopped gradient flow. But early stopped gradient flow is kind of similar, not identical, but like I'm going to start from the origin, and I'm going to start, where's my flow path, that starts from the origin. And again, at first it moves in the direction of high variance, and then in the direction of low variance, and maybe here. And I'm going to choose some early stop point, so maybe this point. So this is kind of my student teacher. And again, the important thing for me is this entire path is inside my legitimate shrink optimal point. Okay, so this is a point takeoff. Now, this student is actually not better than the teacher. It's much worse than the teacher, right? The teacher is this close to the target, and the student is much further away from the target. So this is a bad student, okay? What would be a good student? A good student would be a student whose inductive bias is actually aligned well with reality, okay? So maybe something like this. Okay, so this would be a good student, and if I take my teacher now and project it to the student, or maybe do gradient flow to the, do I have the gradient flow? I don't have the gradient flow. Project it to the student, then I get this point, and now you can see that it really helped me. I mean, this point is actually closer to f star, but again, not more than quadratically. And what we can, our upper bound shows using the random features, that I can shape this inductive bias to get this benefit to be, not the optimal point here, but like close enough to be quadratic benefit. Okay. Okay, but now going back to the question here, all these, the way I drew all these ellipses, they're ellipses centered at the origin. So this corresponds to have some feature space and training those feature space starting from the origin. So this is in the language of training models. This is like I have learned features, and now I'm training the top layer from scratch. I'm taking the top layer starting from 0. I'm just keeping everything in the bottom. Then we learn features. Okay. Another way is to fine-tune the model. So I start from a fine-tuned model, and then I start my gradient flow from that model. Okay? In terms of regularization, that corresponds to regularizing the distance to my pre-trained model. Okay, so geometrically, the way it looks here, I still have an ellipse that covers my effective feature space. But now I don't start at the origin, I start here. And if I do this here, then I project ft to this ellipsoid, I get this point, and that's much closer to the target in this particular picture. Okay? And so in particular, it violates my shrink optimality, right? It's completely outside here, it violates my lower bound. And it's pretty easy to see that this way, I can actually get arbitrary good improvement. In particular, if the pre-trained model was like super close to here, then my benefit would be arbitrary. Okay, does that answer your question? Okay, good. So let's summarize. So yeah, 5 minutes? Excellent. Okay. Okay, so what you should be getting from this talk is two things. First of all, something that, I don't know, I initially, maybe it's surprising, maybe not surprising, is the actual result, which means that even just by being bigger, then you can actually do weak to strong generalization. A big teacher can be, a big student can be better than a small teacher, even if it doesn't have any additional knowledge or search or anything. And also this lower bound, which is maybe more interesting, that says that just by having better features, okay, and if everything is convex, you can only be better. Quadratically better, but not more than that. In particular, you can't have a boosting effect. Okay? Okay, but I think the other thing is really that we have to think a bit more carefully, and goes to the question asked at the beginning when we talk about weak to strong, which effect is coming from, and for each one we can ask like what type of, how much benefit can we get? Okay, so we talked about test time compute and learning from experience to self-play, and from that it's pretty clear that you can get arbitrarily high benefit. You can get boosting, you can have a student, a teacher that like knows the rules of checkers but is really bad at playing and just plays randomly, and it can teach a student that can play perfect checkers. Okay? You even just need search for that, or if you can play perfect checkers, you can also learn a really good board evaluator. Okay. in terms of more knowledge, okay, benefiting from pre-training, the picture already starts being more subtle. So if I do fine-tuning, then I can be arbitrarily better. But if I only use my prior knowledge to adjust my feature space, and I still have a convex model, I still only train the top layer, then I can be better, but only quadratically. So that's already like starting to be an interesting distinction. And then, again, we said by bigger model and more parameters, bigger capacity, I can again be better, which is maybe surprising, not, but only quadratically better. Okay? And I also want to mention here something I think I already mentioned before in response to a question, that there's also another way that we mentioned in the beginning and is more subtle but being better. This if the teacher makes bad choices, I can correct for those bad choices. Okay, I can, for example, if it fits. Okay, I also want to point out that our results, both our upper bound and more importantly the lower bound, are only for convex models and only for regression. And I actually don't know, and I'm really curious, what happens both for classification. I actually, in particular, can you get boosting? If you're talking classification, can you boost a teacher that's like marginally better than chance to a teacher with to a student that has error arbitrarily close to 0? I don't know, okay, with the same setup. And also these the lower bounds are only for convex problems, like linear learning just the top layer. The problem is definitely well defined also for non-convex models. Like if I really go back and train an actual take both layers of a two-layer network or even a deeper network. If I'm training my two-layer network, both layers with gradient flow, gradient descent, or say gradient flow, even in the population with like 100 units, and then I teach it to Zaid's network, which has 1,000,000 units. But can Zaid be better than me more than quadratically? And our lower bounds doesn't preclude that because our hypothesis class is now non-convex, and I don't know if that satisfies specifically for training a network, if that satisfies shrink optimality or not. I don't know what the situation here is. Okay, and I think that's it. You can the paper is an archive, and I'll be happy to take any additional questions.
We had many questions during the talk, so we'll take maybe 2 questions.
Yes.
Do you have a reason to believe that classification? Yeah.
Well, okay. I just don't know. I don't know.
Okay.
I actually, my guess. Yeah. So in some sense, I don't have any reason to believe that. I definitely can't show it. But somehow it might be easier to get a boosting effect from classification, because if you have you can classify still with a lot of error, but be close to the right direction, maybe. You have, like, especially if I look at the way I'm thinking of measuring this is I have to be, what do I mean by that, right? So the way I think about it is that all the training is done on the logistic loss. So the teacher minimizes the logistic loss, and the student does gradient flow for the logistic loss. But then what I compare is the misclassification error rates. And misclassification is non-continuous. And once the loss is non-continuous, then I don't know. It could be very different. That's all I can say. I don't know. I'm not going to bet money one way or another. But all I can say is that it's not that our lower bound extends directly in some way.
Relatedly, I guess not relatedly. This idea that you're not seeing a boosting effect. One thing about boosting is you're going to get different teachers, right?
No, it's the same teacher. Just get it multiple times.
Yeah, but it's reweighted on a different distribution. I don't know.
Okay, I can ask a. Okay, maybe I'll ask a question that maybe this is one thing you could ask, which does happen in boosting. What happens if I repeated this procedure multiple times? So I have a weak teacher, and it teaches the student, and then the student teaches another student, the student teaches another student, repeat this many times. If I repeat it enough, can I get a boosting effect? And the answer is no. So that we can show. You need slightly stronger property instead of looking at shrink optimality, because a shrink optimal for shrink optimal is not shrink optimal. It isn't associative in some sense, or transitive, I should say. But the property you need to do is just reducing the norm, and that's enough to get a slightly weaker but still quadratic lower bound. So that I know at least wouldn't help. Okay.
Any other question? Yeah.
Yes.
So my question is, you answered my first question already. So, well,
oh, sorry, I should have waited for you to
end. But how about you have multiple weak teachers?
How they have multiple weak teachers? What happens if I have multiple weak teachers?
You have lots of weak teachers.
No, that if I have, okay, so if I have, and I think I spoke to you, think about, so definitely if I have two teachers that are, if I have two teachers that each of them has error like 10%, it might be very easy to learn, definitely, okay, maybe even easier. If I have 3 weak teachers that each one of them has error like 20%, just by taking the majority between them, I might be able to get 0 error, right? So if I have teachers, if I learn Romanian from you and French from Zaid, I might learn, know both, and I'll be smarter than both of you if I could actually learn languages, right? So if I have multiple weak teachers, I can definitely gain just by combining between them. In this combination effect, especially depends on the domain, I can actually be, like imagine that I learn Romanian from you and French from Zaid, and then I have a text that's like mixed Romanian and French. So you guys are actually, French is a bad example, but like you'd be completely lost in it, and that would be perfect. So definitely, if you have multiple teachers that teach you different things, you can be much better than those teachers. But that's even without the weak to strong effect. That's just by combining experts.
I was thinking, yes, of course.
Okay,
I was thinking
here
more
in this
like
setting,
you have two teachers who are kind of random.
Okay. If you have 2 random features teachers, then you can. Okay, so if you have 2 random feature teachers, then I'm pretty sure that actually our lower bound. Okay, that's a good question, and I think our lower bound still holds in the sense that if you have, at least if you have a constant number of random feature teachers, you cannot be. Like you get a quadratic with some preterm that depends by k, because again, you're going to be like shrink optimum with respect to some average or something. I have to, or their subspace, I think. And their subspace is not going to be too small. I don't know. I have to think about that.
Let's thank the speaker.
Okay, thank you.